Hey there, my name is Anand Ramakrishnan and welcome to my presentation about harnessing emotions to improve face recognition. Face recognition is the technology of identifying an individual from their image. Current face recognition technology utilizes large-size data sets that consist of millions of individual faces. These data sets are used to train deep neural networks to create a face embedding space. A trained deep neural network scans a face and creates a vector representation of the face. This vector can be thought of as a point in a space called as the face embedding space. While training the deep neural network, the face embedding space is created in a way such that similar faces lie closer to each other and dissimilar faces lie farther away from each other. The motivation for our work comes from the observation that the embedding space is pretty unorganized, i.e., there is high intra-class variance. A second observation is that there is large amounts of additional information, such as emotions, that is not used while creating the embedding space. So our research question at the beginning of this project was, can we impose geometric constraints to create a better organized embedding space utilizing emotion labels of the faces? And by doing so, do we obtain a boost in accuracy in the face recognition task? So in this work, we introduced secondary loss functions to change the unorganized embedding space to become more organized. In particular, we introduced 4 different secondary loss functions and we evaluated it individually and in combination. One of the loss functions that we created was the fixed basis vector loss. Here, in our implementation, we had 2 parts. First, we forced the formation of mini clusters using the emotion labels as presented for the faces. And secondly, we force the mini clusters to align themselves towards a fixed basis vector by defining it from a central cluster. As seen in the image, our central cluster selected was the anger cluster, and we forced the emotion clusters happy and sadness to be placed at a fixed basis vector distance from these angers cluster. Results. We evaluated our model on several testing datasets. For training, we trained our models on several large datasets that consisted of hundreds and thousands of individuals with millions of images. For evaluation, we perform a qualitative and a quantitative evaluation. For the qualitative evaluation, we provide the principal component analysis of the embedding space. And for quantitative analysis, we provide the ROC AUC scores and true acceptance rate at a particular false acceptance rate value. Here is the principal component visualization before imposing geometric constraints. As can be seen, there is high intra-class variance in the embedding space. Here, we see the PCA visualization after imposing geometric constraints. As can be seen, it's highly organized and there's low intra-class variance. Quantitative results also show our methods generally outperform when geometric constraints are placed in the embedding space. In conclusion, we created several novel loss functions that impose geometric constraints on the embedding space utilizing emotion labels. We illustrated how they help improve face recognition. We also saw that strict geometric constraints on the embedding space improves the accuracy of face recognition substantially. We hope to utilize this technology to provide teachers in classrooms with feedback about their interactions with the students. Thank you.